Thank you very much, Stefano, for that. So yeah, I'm Will Skipper, and I'm presenting particle characterization of rail sand for understanding tribological behavior. I'm sponsored by both the EPSRC and the RSSB. Yep, so to run through the contents of my talk today, I'll do a little bit on the background of sanding for the very few who don't know what that is, a little bit up the aims and objectives of my project, and then race through particle characteristics, the characterization method slightly, and also comparing some example rail sands that went through this characterization process. Then lastly, I'll be summing everything up at the end. Right, so for those of you who don't know what sanding is, when low adhesions on the rail, such as leaves and wet rail, as we've had a lot of this past couple of days, you can use sand to try and boost back the adhesion again. So it's usually a train-borne system, such as this beautiful diagram here shows. Sand comes out of this hose and into the contact here, and possibly providing some sort of mechanical link and also cleaning off contaminants. There was an RSSB study which predicted that low adhesion in the autumn time cost the UK £350 million per year. So even a small increase in sanding's performance can potentially save millions of pounds. Okay. So the ultimate aim of this project was to use a particle characterization framework to assess different sands and also have a brief look at their tribological performance with some sort of preliminary study. So, to quickly say what the objectives were, I had to identify the key particle characteristics from literature. I needed to identify and conduct characterization tests to find what these particular characteristics, properties were for 3 different types of sands. And lastly, I conducted some small-scale tribological testing on these sands. So to briefly run through what particle characteristics I was looking for. So obviously the geometry is very important in sanding. So both the size of the sand and the shape. And I did this through 2 different methods. Sieving analysis for the shape, which I think we're all familiar with, and some 2D image analysis. So I've put an example here. If you imagine this is my particle, beautifully drawn as it is, and then you could compute it to a circle with equivalent area to this particle, and from that you can work out the sphericity by comparing this particle to the actual particle and also the circle equivalent diameter as a size measure. So I also looked at mineralogy, which is quite simply looking through an XRD and then trying to find what sort of mineral content is in there, for example quartz. And then physical properties also went into a little bit. So I looked at density using a water displacement method. I had a look at hardness using both nano and micro indentation. And from this micro indentation, I also looked at fracture toughness. So creating cracks in my specimen, then measuring off those cracks to get an idea of what sort of fracture toughness I have. And lastly, I looked at 2 things which were more applicable to rail in general. So flowability, so how easily it can flow. You don't want a sand that's just stuck in the hopper and can't come out. So that was done through an angle of repose test. So essentially, what sort of angle you need to get it to begin flowing. And I also looked at a coefficient of restitution, which is a fancy word for a bounce, how much it bounces. And I looked at that through a high-speed camera and tracked it in 2D, how it bounced off an actual rail. Okay. So the sands I looked at. So I looked at CM2018, which is currently, or was currently, UK standard that was being used. I looked at some sand source from a Central European company. And I also looked at Ulegrave 110, which has been used in previous sanding experiments and comes from a Derbyshire quarry. So to quickly run through the sieve analysis, the Garside, or the UK rail sand, was the largest, and the Ulegrave was the smallest. All these sands were within UK standards, I believe also all within German standards, and some but not all were within French standards. So you can see here, this is just percentage passing graph, so they all come up and all quite steep, quite uniform sands. I also conducted image analysis, which I explained briefly before. So this backs up the Sieve analysis for all Yule groove sand is the smallest, Garside sand is the largest, with the Central European sand being roughly in the middle. This just corroborates what the Sieve analysis found. And I also looked at how circular they were, so comparing that round particle compared to my actual particle. Both the Garside was very circular, I found, and then the Central European sand and the Yule groove sand were slightly less circular. And lastly, they're all fairly non-convex, so that means it's all quite rounded edges, if you like. I won't go into the details of what exactly that is. So, looking at it through diffraction, both my Central European and the Yule groove sand were both 100% silica, with the Garside sand being about 90% silica. I think this is definitely for UK standards, passing the norm. I believe there's something about it in the French standards as well. Yeah, so looking through the density, all the densities were quite similar, about around the 2.65 mark, which is what's reported in literature. This density isn't particularly interesting as of now, but it'll be more when I expand this onto different particles that we might see something of interest. And the hardness and fracture toughness results were all very similar. Again, they're all quartz sands, so this isn't that surprising. There's quite a lot of variability here, especially in the nano hardness and the fracture toughness. The nano hardness, it's comparing local areas, so it's going to be influenced by one particular area, maybe having a slightly different morphology to the other, whereas the micro hardness takes it more as a whole and obviously indents a larger area. And the fracture toughness is reported to be quite inconsistent at times, so this was no surprise. So to go on to the angle of repose, I looked at the angle of repose under 3 different moisture contents. So 0% or about 30 degrees was the angle at which they started tipping out. At 0.2%, it didn't really seem to make that much of a difference. But as soon as you added 3% moisture content, it rose quite dramatically, especially in the case of the smaller Yule groove sand, possibly because of its larger surface area compared to its actual volume. Yeah. So to go on to the coefficient of restitution, so they're all fairly similar sands, but with a large degree of variability in it. I'll talk a bit more why I think that is later, but it's partly, this will be, again, of interest when I bring in more different particles and have a look at what happens to them. So, lastly, to go on to the tribology of it all. So, I used a high-pressure torsion machine to look at these. So essentially applying 900 megapascals of pressure and then twisting until you get some sort of dislocation through a set motion. So in this case, 0.4 millimeters of displacement. I looked at this with a dry contact here, which produced a very high coefficient of traction, which you see here. And I also looked at this with wet contact. So this blue line here was just wet with unsanded, and you can see that gets quite low. But when the sand is added, so it all seems to improve the adhesion performance, with Garside and the Central European sand performing best, with the Yule groove sand slightly below. Yep. And I also looked at this with leaf extract. So taking some leaf-soaked water, applying it to the contact, and then seeing how the sand affected it. So again, it improved the adhesion in all of them, with the Garside sand especially being the best from what I found, and the Central European and Yule groove sands also improving adhesion as well. Yeah, so to compare the rail sands we've looked at, all the sands were very similar, to be expected if they're all being used by rail industry. And also similar constituent materials. I think there's a belief that harder particles usually work better, which I think is shown in someone's talk today. So large variations were present at both the indentation and coefficient of restitution tests. The indentation test is a standard test, whereas the coefficient of restitution test might be able to be improved by using a 3D measuring system as opposed to 2D. So, yeah. And also, with the coefficient of restitution, you can see here, if you have two different particles, this one here, a more rounded one maybe, tends to bounce and come straight back up. Whereas this one here, it hits it at a certain angle, imparts spin onto it, and it keeps lower, which is potentially what is more desired in the sanding relationships. You don't want all your sand bouncing away and out of the contact. And there also seems to be a possible relationship between sand size and traction restoration, which has been found in literature before, but it was good to see that on the HPT test this was consistent. Yep, so quick conclusion. So I've presented a rail particle characterization framework, which I'll hopefully be able to take forward and use for other different particles and more extreme cases other than just sand. Yeah, so more particles will go through this in the future. And small-scale tribological tests suggest a difference in sand performance based on, I assume, size, as this was the only real differing factor between the three. Okay, thank you very much.